Okay, so good afternoon to everyone. We will start this afternoon lesson with the first set of slides regarding the requirement analysis. So we discussed about how to design your software, in particular your real-time application and system, but it's critical also to understand how to define functional requirement and the other kind of requirement that you need when you are designing not only the application but also the system. Okay. In particular, there is the need to establish the role of the requirements and how we need also to test our requirements and our application. In particular, some method for collecting this kind of requirement, and we need to avoid redundancy, omission, and in particular inconsistencies when you are asking for requirement for your application. Also, we want to go to a formal model that uses some kind of assumption or assertion, some conditions, break, post, invariants. Also, some finite state machine models. Do you know what finite state machines are? I suppose that you've already seen these in other courses. If you are fine with that, we can skip a bit about finite state machine models, but we need also to take into account how to model them and to automatically generate some kind of code from this kind of models and other kind of diagrams. Also, we can link one or more test cases to some kind of requirement. We will see some kind of example of this. And also how to move from requirement to implementation. Do you know what this is? The classical V of implementation. It's a V model because it starts from the requirement and it goes to the validation through from requirements, functional specification, modeling, exploration of the architecture, modeling of the components, of the behavior, then the coding is down there. Then from the coding we go up again by testing our modules, testing the integration in the system, checking that the whole system is verified, and then validate against real data, a real case. So, user requirements should be something that describes our system and what our system is supposed to be able to do. Okay. But also what is its behavior and not how it will do it. Because usually it's us that define how the algorithm works. The requirements, the user just needs to tell us, okay, my machine just has to do this. We will state, okay, you will do this using some kind of things. Let's say you ask me, I need to reorder this thing. I will tell you, I will use a merge sort, I will use a quick sort, I will use something like that. But if you ask me and you tell me more requirements or more specific of the data, I can use something different like bucket sort or something different again, because maybe it's not numbers but it's text that they have to reorder or something like that. Okay? In the V model or in whatever cascade model, requirements are the starting point. So we will start from the requirements. And you don't design anything if you don't know what you are supposed to be able to obtain. That's somewhat clear. Also, you should not argue, but somehow discuss with your customer. Okay? And it's better if they are communicated in somehow very plain language, because otherwise it becomes very more technical. Just from the requirements, you will go down and become crazy when you're trying to translate technical things into requirements. If I tell you I need to do this, this, and this, it's better if I state, okay, A, you need to do this kind of interaction with this kind of hardware. No, just tell me what I have to do. Then I can care about the other stuff. Unfortunately, natural language is subject to ambiguity, misinterpretation, or something like that. So every time we have some kind of this, we need to ask. Okay? Requirement analysis is quite often the result of empirical process which has imprecision, subjectivity, and so on. That's why some kind of model has been developed, like the film state machine model and so on, to be able to exclude some of these problems. Also, most of all of you are engineers, therefore you are technical people. But sometimes your user asks you for something is not technical. So you have to communicate and to learn how to communicate with non-computer scientists and people which are not using technical languages. Let's say that you have to set up something for someone who is a gardener who needs to create a real-time scenario for the automatic watering of a very big system or something like that. He doesn't know anything about computer science, but you have to understand what he needs and to model. Also, we need to describe the specification of the system in some formal way. In addition, sometimes requirements are not defined, are not known, because you ask, okay, what is the kind of data that I'm going to, I don't know. We still don't know. So you have to be open and model your design in some way to be able to move and change things along the way to when the requirement becomes more clear, and then you finish to specify what happens. Okay, so it's a trial and error process. And requirements are alive. You will, if you are going into enterprise and not or even in academia, but in particular when you're going in factories, requirements are evolving. One day you're starting with some machine that needs to do A and B. 1 week later it has also to do C. A couple of months later it doesn't need to be able to do A, because we bought something that does A, you have to do B, C, and probably D even. So it's crazy, in particular for software people, this is mind-breaking, because you are starting to create a model of your system and then someone changes your cards and it becomes very crazy. But this is why we need somehow to summarize in a schematic all the requirements that you are constructing and getting from the customer. I think some of you know this kind of comic strips. No one? Requirement documents are produced most of the time after the system is developed. Why? Because we, as developer, write down, we document our function, our code, and we say, okay, my code can do this, this, and this. But this is not the requirement. This is what your code is actually capable of doing. It's better if the customer tells you what the system has to do and you design the software as it is. Okay? So, what are the objectives in our approach? We need clarity, completeness, possibly avoiding ambiguities and inconsistencies, and redundancy. Okay, if you want to avoid possibly these three kind of problems, and we want to be as clear and as complete as possible. We can use different techniques depending on what we are doing, what we are using. We are using an embedded system, we are working with a database solution, we are using functional programming or object-oriented programming model. It depends. So depending on what you are using, what you are supposed to be able to do, also this kind of techniques can vary. Okay. These kind of techniques can be classified according to the different starting point of the analysis, because we can start working the mode of the states of our final state machine, the model of the data, so we know everything about the data that we have to handle, so we somehow build from that. We have a use case, so we know that this is what is working on, so we need to change it to be more, let's say, real time or more efficient or more, we have more throughput or something like that. What are usually the reaction of the system? I don't know why this is Italian, but whatever. The activities that the system is supposed to accomplish, and the reaction or the entities or the actors that we interact with our system, and the event in which the system must react. Let's suppose we have an autonomous car. We have to know which are the actors that we interact with our car, probably other cars, the environment such as the traffic lights, the signs, and so on, but also we have other entities like other cars, people, pedestrians, bicycles, and which event the system must react. We find a pedestrian in our way, what we have to do? We have to stop, we have to go on, depends, whatever. And also, in the end, the objective that the system must satisfy. So, our concept for now is we have to be able to write this requirement in somehow a structured natural language, not a page of things that we are writing down, but a schematic. We have to enforce this writing style to tend to a finite state machine description. So we are able somehow in our mind to translate from this page to a finite state machine. Enforce the use of data like dictionary possibly. Also use some simple rules to avoid redundancy, but this will be clear in a couple of examples that we will see later. Refine our text with diagrams, so we are able to construct a real on-the-fly machine or diagram, which is a semi-formal approach. And in the end, it will ease the definition of the requirement-driven test cases. Some kind of formal way to do this is to group our requirement as they were some kind of chapters in a book or sections, so that we have which are referring to which are the level of the system, the inputs, the outputs, the works, the algorithm, and so on. And in each section, we can place the requirement that apply to each working mode. Let's say that also a car can have a working mode which is idle. What it will have to do when it's in idle? To which kind of input does it have to react? Well, when we turn it on, or when something around it happens, because it may be that even if it's in idle state, it may have some kind of sensor active, and if something is happening around the car, it may react to some of this external output input. Okay? Generally, at least a subset of the system does not happen in isolation, because we have things that trigger multiple takes. Okay, we have events that trigger multiple takes. But we need to have a protocol of sequence and event of these reactions. So the finite state machine model. The scenario that we will define in the working, that we define the work of the user of the system can be organized in sequence diagrams. I think that all of you also have followed some software design courses and know what UML is, right? So we can have message sequence chart and so on. Also, the requirements express the large-scale partitioning of our system. So in our system, we can partition from whatever is the memory requirement, the hardware requirement, the input, which are the sensors, the output, which can be also actuators, and so on. Be aware, functionally, not physically. So what is the input path without knowing which sensors are in there, and so on. And this partitioning should highlight which is the definition of the input and the output, not only in the full system level, but even in the subsystem one. So we know that we can have cameras and radar, let's say, in a car, but whatever, we can have also output from the external cameras, which are not just the images, but some metadata which have been elaborated from some kind of input smart sensor. Okay. Data dictionary. In the definition of our case studies, we can also have the activities and the states of the system. And for different kind of inputs and outputs, we need also the parameters necessary to refer without possibly ambiguity, because we can always have some kind of using the same name for different things. No, we do not need this. Also, we should avoid having the same name. So we have to put some kind of prefix or postfix to be able to discriminate to whichever variable is in from whichever state machine is this variable attached to, and so on. So in this case also we do not refer what are concrete types, whatever, what is the size of an integer, which is the size of a floating point, and so on, but we consider real integer, whatever more abstract way of defining it. If you can read this and understand what it states, please tell me. How many times it says that you cannot do anything for the next 5 minutes? Cut too much, right? Also it states that you are not able to do anything because you are locking the boiler and you have to wait 50 minutes, and it's stated twice here and twice with this, and this, and this states that you have to wait. Okay. Just tell me one time. This is redundancy. When something is telling it and trying to explain you how the system is working, if it's doing something like that, stop it and tell me each time. One, put it in a schematic, and if you are finding it again and you are telling it again the same thing, don't do it. Okay? It has a necessary description because we don't want to know what the system doesn't do. We want to know what the system is supposed to do. Okay? Of course, our boiler shouldn't fly, and so on. Also, it's easier to state if the interface is off and all LEDs are off, then button presses doesn't have any kind of effect. If you are in setup mode, pressing the according button has no effect. Okay. Also here what we have? Power failure, restoring power, unlocking, resetting, shutdown, startup. Which cause of error? We need to define and specify what are these errors. It's a problem of water error, water supply error, water leakage error, or gas leakage error, gas supply error, high temperature error, low temperature error. Okay, these are clear. But if I say error, whatever error signal, it's not clear for me if I have to write down and some kind of code. Okay? How can I identify the highest LED in this setup? It's not clear. Is the highest between the button? is the highest related to the highest temperature? Not clear. How many kind of temperature are supposed to be in the system? All of these are temperatures. So we need to define a schematic in which these are clear. So we can maybe use UML or other kind of mechanism, languages, designs, methodologies, and so on. In particular, we already told that user requirement and functional requirement are different, right? User requirements are a set of high-level requirements perceived by the final user of the system, and they are used to drive the feature design. So we have the interaction between the user and the machine and the system. On the other hand, we have the functional requirement that needs to address which are the mechanisms and the procedure that the user needs to do to obtain its result. Okay? We can have document templates, rules for writing our natural language, and also versioning, tracking, and so on. We can have user requirements, functional requirements, safety requirements. Let's say for a boiler example, safety requirements are that it should be able to be opened if the temperature inside is too high, or it's not possible to operate or ignite it if there is a gas exposure, and so on. We need diagnostic because the system needs to test itself to check if something is working or not. Something like parafunctional requirements, so a set of requirements that address feature characteristics like timing, usability, scalability, speed, something that is not related to a single system, but more to whatever we are using for a large system or a replicable one. Okay. Also, we can have the state chart diagram, which is like a flow chart. A functional context diagram, which is the listing of all the external I/O signals in and out for each feature. Left side has the input and the output, right side, only functional. And sequence diagrams scenarios. Again, all the requirements should be unique and identifiable. Okay? Also, they should be testable. We will come back about testing a bit later. We will see about that. Also, please use these verbs. Should, must, will, should. English is very clear about these four words because should is mandatory, must is an assumption, also mandatory, but should is something that is going to do. Must is an assumption beforehand. Will is guaranteed to happen, and should desire but not required. You should not write negative requirement, as already stated, and this should be for the inbound and outbound state transition. So not the internal ones, but just only the external ones. So the one that are with the user, that the user will use and that will interact with. Also, sometimes it happens that we are writing down a contract with some people that we are working for and writing our code to. So the system may be considered as a contract between the let's say, one of the subsystem and the environment which are other subsystem. Okay? So, if we are stating these things should work like this, any other subsystem that is working alongside him will continue to do that. So we have a set of assumptions of our environment with the other subsystem. It's like they all agree to work in some way, but they have to agree on how to work together, because otherwise they will crash somehow. The work will not go straight. And we can specify formally or informally this kind of assertion. We talked about precondition, postcondition, and invariance. So the precondition needs to be verified in advance in our system. Postcondition are guaranteed to be true after the reaction. Let's say I find a pedestrian in my way. A postcondition is I'm stopping if I'm not able to if I will reach the pedestrian, I need to stop before reaching it. And the invariants are going to be always true before or after the action. Let's say if I turn on off the machine, it will have to it will be able to continue to work even if I turn it off and on again. Okay. This is DOORS, is a program that is able to construct this kind of requirements. It has hierarchies and manages databases of requirements. In particular, as you can see here, it creates chapters. So we have introduction, types, requirements, capability, carrying, the number of people, amount of luggage. Let's say we have here some kind of travel system, flight system or something like that. And then allows more attributes for our requirements. Let's say the number of people, how much people can be able to be used, the amount of luggage for each people, 1, 2, 0, and so on. Also, user should be able to carry to 100 kilograms of luggage, and so on. So we can change this kind of things. Also, it's desirable and mandatory. So these need to be able, the system needs to be able to do this. It should be able to do all of these kind of things. So, as you can see here, we have item, user requirement 18, user requirement 19, and so on. So we have a set of requirement items. Any requirement referring to a reaction of the system may also need to be refined, highlighted, and so on. Because it needs to understand which are the assumptions for that requirement, the precondition and the postcondition for that requirement. Okay. Also, for each reaction, we need also to state which are the independent from before and after. It's useful to ask to our customer, if he knows, what should be the reaction of our system to some kind of possible error condition. Borderline cases, exceptions. What happens is if a cat goes in front of the car instead of a person, or something like that. What happens when there are more conditions verified or more problems to verify at the same time? And this enhances the robustness of both our design and our future implementation. Because we know what should happen in this condition. And we are able to code everything that should happen. This is another example of what can be seen as a requirement analysis for temperature setup in the boiler. And we have all of these things which are stated here. This is clearer for sure. So we start from the user requirement. And using the user level input output and the use cases, we are able to write which are the validation tests for the system in the end. But also we derive the functional requirements. From the functional requirement and the signals, the event, the system levels, event and MC, we can be able to verify the system. Not to validate on real case, to verify if each subpart of the system is working as supposed with every kind of input and output. Then we design these different kind of models, behavior, structure, we code and we create a structural test for each thing, for each function that we are going to write. Also, if you are doing a very good job, we connect each of our functions or each of our modules in our code to a specific requirement. So the requirement goes to a design element and that goes to a code section. Going back from down to top to a code section, we can relate to a design element which relates to a user requirement. Do you know about Mars Polar Landing? I already told you about this. It was launched on 3 January 1999. It arrived on Mars on 3 December 1999. It was supposed to land near the south pole of Mars and to dig for water, in particular for ice, because on Mars there is ice, with a robotic arm. But after the initial phase of the descent, it stopped the communication. Why? We don't know actually what is the cause of this, but we have many candidates. Most likely, it's possible that the engine shut down beforehand due to some noise on the sensor that have on the legs of the module. It was not designed to send the telemetry during the descent of the planet, which has been severely criticized by the review boards. It wasn't a requirement. If you wanted it, you need to require it. Which are the causes? The lander failed to separate from the cruise stage. Plausible, but unlikely, because it's constructed like this. We have the lander inside and the heat shield and the back shell, which should decompose during the landing phase. The landing site was too steep. Okay, it's plausible, but if you have searched for the landing site for so many times, it's unrealistic. The head shield failed. Okay, plausible too. It happened many other times that the head shield didn't manage to deliver the actual protection to the instrument. Loss of control due to dynamic effects, also plausible, because the atmosphere on Mars is very different than the ones on Earth, and is not so easy to understand and to simulate, in particular in the early 2000 years, to be able to do this. Loss of control due to the center of mass shift, something moved inside the module, and so the center of mass, the barycenter was shifted and the whole thing started to roll. Most likely it was the premature shutdown of the descent engines. Also, the parachute drapes over the lander. So if the parachute goes over, it shuts down the communication of the lander because it's covering the antennas. Or the back shell hit the lander when it falls. Also plausible, but very difficult to happen. This is what happened probably in real. The magnetic sensor on each of the legs need to sense when it touches the earth, the mass, not earth, the land of mass. Legs unfold at 1.5 kilometers above sea level, above surface. Then the software accepts transient signals on touchdown sensor during unfolding. So when the legs moved out from the structure, there was the sensor on the legs that registered some kind of connection, collision. So it said, okay, I'm touching land, stop the engine. Not a good idea. The system requirement to ignore the transient signals was not defined. They didn't think that it may happen that during the extension of the leg, it may happen this kind of noise of touching something. The software requirement did not describe this kind of effect, and the engineer presented the code inspection of the source code that was running on the lander didn't understand the effect of this kind of scenario. And it wasn't caught in testing. Why? It wasn't the requirement. Therefore, no unit test was written to check this kind of scenario. Also, the sensor might be improperly wired during the integration test. So, no touchdown was detected during these tests. It was probably 40 meters above the surface, traveling at 13 meters per second, which is kind of a lot. This estimated impact velocity was 22 meters per second, because without the rocket engine that was lifting and slowing down the fall, any spacecraft wouldn't survive this, and probably the nominal touchdown velocity should be 2.4 meters per second, which is one order of magnitude less than the actual one. These were the system requirements. The touchdown sensor should be sampled at 100 Hz rate. So we should have a real-time task that checks 100 times per second, which is the state of the sensor. The sampling process should be not here. Okay, should be initiated prior to land entry. Sorry. Okay, here. To keep processor demand constant. Why? Because there was a very low power CPU, so we do not want any other kind of sensor of task to check the sensor to run while it's not useful. We have to remember that we need on this kind of system to keep the lower possible the requirement of energy. Okay, because we do not have big batteries to rely on. In particular, in space, we are not able to recharge our battery if we do not have the sun or light panels. However, the use of the touchdown sensor data shall not begin until 12 meters above the surface. Whoops. If you are 12 meters above the surface and you have elongated your leg before, this should happen. This is what happened. Okay? But this was the system requirement. And this is the flight software requirement that has been converted. This is natural language, this is being converted to processing. The lander flight software should cyclically check the state of each of the 3 touchdown sensors, one per leg, at 100 Hz during landing. The lander flight software should be able to cyclically check the touchdown event state with or without touchdown event generation enabled. Upon enabling touchdown event generation, the lander flight software should attempt to detect failed sensor by making the sensor bad when the sensor indicates touchdown state on 2 consecutive reads. Also, the lander flight software should generate the landing event based on 2 consecutive reads, indicating touchdown from any of the good touchdown sensors. This means that if any of the 3 sensors has been labeled as bad, or any 2, and the remaining one kept saying, okay, I am touching the soil, the engine will shut down. Right? But this wasn't tested. It wasn't supposed to be tested in some kind of scenario, in particular for the 12 meters above the surface. Do you see this reported in this? 12 meters. Anywhere here there is the 12 meters reference? No. So this was an error of translation from human, let's say natural language, to software requirement. This is not correct. This was missed, untested, and it compromised the issue. Also, use some kind of versioning to check if the requirements are changing. And if a requirement is changing, you have to change all the chain of the V. So if the user requirement is changed, then you change the functional requirement, then you change the design, then you change the code. Don't start, okay, the user requires something different, I will change the code. No, you have to go down all of this. Okay? Or, if you just change your design, change the sub version. Version 1, version 2, version 1.1, I just modify the design, not the requirement. You can have, for a final state machine, something like, I'm entering in this state, while in this state, I check for some things, and when I exit, I check for these exit states and conditions. While I was talking about changes in the environment. This is what happens most of the time. They doesn't share with people who write code what has changed in the project requirements. So in the end, the system doesn't do what the people want to do. Okay. Continue to communicate with the people, with the customer that asked you your system. Another thing that happened in the past. Ariane 5. It was an European system that was supposed to launch satellites or other things in geostationary orbit. In low Earth orbit. You know what is geostationary, right? Satellites that are continuously spinning at the same rate on our Earth surface. In an orbit, low orbit. It took 10 years and cost $7 billion. Not bad. Problem. First test flight, self-destruction in 37 seconds after the launch. Great. Why? Well, the Ariane 5 software used the same specification of the Ariane 4. Because they say, okay, we are creating a new version, let's start from the old ones. Why? Not a problem. But the Ariane 5 flight path was different, and also behind the range for which they used the code was used for the Ariane 4. They used, let's say, different sensors that had different ranges. What happens is in my variables, I got a value that isn't supposed to be in the range, let's say, of the values that I'm checking. Whoever knows. Okay? The greater acceleration caused the backup and primary inertial guidance computers to crash. Because it was probably to a segmentation fault or something like that result in a function. And the launcher nozzles were directed to spurious data. Therefore, it started to create some kind of turbulence and it exploded in the air. The error was not discovered before the launch of the system, because the pre-flight test has never been performed on the new source code. They stated, okay, just put the code in the new platform and don't try it, just launch the rocket. Not a very good idea. This can be the same itemized requirement for the boiler example of before. We can have the temperature setup mode in which we entering while and exit from the mode. And we have temperature, temporary set point, temporary user set point, and so on. And this is the state machine associated. Enter, while, exit, with its conditions. We can use English to convert this requirement to a formula. We can use logic and or so on, or control mode. The same for safety requirements. We can create the model, and then we have the test. The test, I told you that we have the precondition and the post-condition for every kind of input. Precondition, post-condition. Okay? What happens? What should be the state before? What should be the state after the input? Okay. 5 minutes stop, and then we go with the functional testing. Okay, so we talked about the design and testing. In particular, now I want to go a bit deeper about testing. The objective is to learn when, what, and how test. Which are the usual practical test techniques, the theoretical basis of testing somehow, and the defining use of what are usually called black box and white box testing. To learn about the coverage criteria for the testing, so how we cover every possible data, understand the conformance of this testing, define the methods for the unit test, and to learn about the connection between tests. Okay, so many things. testing is on the right-hand side of our V model. Right? The assumption for the functional black box testing is that the software is a function that gets output from a specific input. It is used for the system level testing and for unit testing. It is requirement driven, so if we have to define the requirement to be able to do this kind of black box testing, because it covers aspects of the specification that we made in the previous, that I explained in the previous hour. It can be also enhanced with this information and is implementation dependent, because it depends on what we are implementing, in which language we are using, and so on. Also, and usually it's better, tests should be planned beforehand. Nevertheless, black box testing is not completely sufficient for all the testing purposes that we need, because it doesn't detect introduction or unintended functionality. So, let's say an hacker that wants to break our system, that may change the that wants to change the functionality of our system, usually black box testing, functional testing, is not able to test this kind of introduction to our system. And also is somehow difficult to perform, because we need a lot of coverage of the input-output space. Better is the white box testing, the structural testing. It's based on the structure of the program model. It somehow tries to understand what is the complete structure of your code, and is defined to satisfy what is called a coverage metric. Somehow is like the test that Professor Bertoni told you about, the schedulability test or something like that is somehow similar to a structural test, because it allows measuring the progression of the test, so the amount of coverage of how much of our system is ready and safe. Can be complex. In particular, the 100% of coverage is sometimes unfeasible to program and to create, and is incapable of detecting errors of something that we forgot to implement, like the 12 meters rules of the example before. There is also a model-based testing. Given a model specification, in which we know, which is the transition diagram, we are able to create simple boxes that checks for each one of these states. It's called a fault detection or a machine verification. We observe the behavior of every one of these states. Unit testing. Who already heard about unit testing? Not in this course. Some of you, okay. Are programs and sometimes utilities that allows the user to create tests to be applied in the so-called continuous integration development mode. These slides are taken from these lectures of University of Technology of Eindhoven. We are talking about the black box that I just showed to you. And we define the use of this function with nominal testing, boundary testing, robustness testing, equivalence, decision table, and classification trees. These are all mechanisms to check the input and the output of our functions. So we have input, we obtain output. We have input ranges defined with E, I, and D of Y is the range of possible values of IK. Is mostly impossible or impractical because it takes too much time to check for all the possible combination of input because it's combinatorially exponential. For each of these possible values we have to check for the Cartesian product of all the possible intervals. It's not easy. We need to choose some of these values, right? We can select a value in the range of the admissible ones and maybe some of out of the possible range. We can select randomly, choose directly some kind of typical values, but most probably we try a very small fraction of all the possible inputs, right? What are the most meaningful input from your perspective? Open question, please answer. Considering these from min to max and these from min to max, two possible ranges of the variables, which are the most meaningful?
The one in the middle, between min and max.
The one in the middle, okay.
On the edge of the range.
The boundaries. The boundaries. Because we have as input, I said, the Cartesian product of all the possible values. Okay. But our domain is from independent values. We suppose that each of the input is independent from the other inputs. Okay? So this is what we start, our assumption. And we have many kind of variables, type of variables, because we have Boolean, discrete, integer, continuous floating point or something like that, ordered, and so on. Most errors occur on the boundaries, on the extremes. Probably because we mistake a less with a less equal, or something like that. The counters of my 4 is off by one value, or something like that. This is also called stress testing, our application. And is also applicable to range boundaries. So we choose 4 candidate values for each input in the range A, B. We choose the two extremes, A and B, near the two extremes, so the predecessor of A and the successor of B, and we choose nominal values for all other values. A set nominal, consider a set of fixed value for the other variables. Okay. We use the single failure assumption. So we assume that our code is not working for a bug, and each failure is the result of a single bug. Not always true, but we can suppose this. Assuming we have n possible input variable, with this test mode, boundary testing, we need to do 4 times n plus 1 test cases. Example of computing a mortgage. Mutuo. We have to write a program that takes string, which is the gender, male or female, which can be a boolean. The age value between 18 and 55, the possible salary between 0 and 10,000 euro per month or something like that, and output the total mortgage for one person, which is the salary times a given factor. The factor is given in this table. The table, as you can see, states that there are three categories: young, middle-aged, old, for male and female people. Okay? And these are the possible factors. This can be a solution. Do you recognize the bugs from the source code alone? You do not have, you should not write code like this, okay? You need to write clear and understandable code. This is like obfuscated C code, somehow obfuscated, okay? But using if, using this kind of syntax is way more unreadable than just using if else, right? So instead of doing this, write a page of code with a modification and the tree of if and then else, but don't do something like this, because you are not able to check for all the bugs. So the age extremes are between 18 and 55. So the near extreme should be 19 and 54. So 1 plus A and 1 means B. Nominal value 25, because we choose to take a middle value nominal for this. Salary, the extremes we have said like that should be 0 and 10,000. Near extremes are 1 and 9999. Nominal value between 5,000. Male, yes or no? We assume nominal true. If we do not have any boundaries given, we have to define these boundaries. Okay? So like 0 and maximum int for integer value, 0 or minus double max and plus double max for double decision floating point numbers, and so on. This is the unit test result. 18, 19, 25, 18, 19, 25, 54. 55. These are the, given this nominal male, this nominal 5,000, these are the possible age values. And we obtain correct for all of this. These are the checks for, this is fixed, this is fixed, this is salary, 0, 1, 9999, 10,000, right? And we pass. Female, 25, 5,000, failed. Something is wrong in our code. We failed this one. It's somehow strange using this for Boolean, because you just add true or false, so you don't have boundaries for this kind of, you just have two values, okay? It's better to use the decision table based technique that we probably do not cover this time, is not suitable in this case due to the dependency between age and gender. If you check better this table, if you are male, you are old, you are considered old later than female. You can see here 50 is the maximum for female, 55 is the maximum for male. Okay. Also, we need more combination to check. Just wait for a couple of slides, we will see that later. And a final partitioning. We want to be more robust against possible variables, errors, input errors. We add two more candidates, which are just beyond the extreme. So we are supposed to go from 0 to 1. We check for the previous to A and the next to B value. It's tricky to predict which should be the correct output, but it's suitable for programming languages which have weak typing. Why? Because C and C++ has strict typing, but other programming languages have so-called weak typing. So a type of a variable is not clearly defined until you check for that variable or you put a certain specific value into it. Also, Boolean for C is not a real type because Boolean in C standard is just integer, a type level integer. Okay. So in this case, you have to take 6 times n plus 1 test cases. As you can see here, we fail all of the values. Because in our code, we didn't check for this kind of values, right? As you can see here, it is supposed to obtain nothing if you are younger than 18. You are too old to ask for a mortgage if you are 56. You don't have an invalid salary if you are paying to work instead of having given a salary. And you have too much money in this case, but why I'm having this result? Also, we have multiple fault assumptions. In particular, a fault may be the result not only as the assumption that we made before of just one bug in our software, but a combination of multiple errors. So instead of using a nominal value for the not considered variables, we use the combination of all 5 values for all the variables. In this case, unfortunately, the number of tests that we need to check is 5 to the power of n. In this case, it's 5 to the power of 3, which is still reasonable. 125 checks to be made, right? Consider to apply the worst case to also the robust testing. So we do not check only the interior points, but also the exterior ones. In this case, we have the combination of 1, 2, 3, 4, 5, 6, 7 possible values for each one of our variables. 7 to the power of n test cases. Because we are applying to the boundary value both the robustness and the worst case scenario. Maybe we can also have some kind of errors with some of the values which are not in the boundary. So we can combine this with some randomly selected values. And the number of tests that we have to do increases. Otherwise, we can use some knowledge. If we know that the domain shouldn't have some kind of strange behavior, we can find which are the corresponding boundaries for the internal variables in combination with the techniques that we mentioned before. So we know that this kind of input could break our algorithm or are the most used in our case, so we want to test them. Somehow less covering test case or unit test methodology is the equivalent classes method. We divide. For each of our variables, we divide the interval of that we define for from the boundaries, and we try to cover the equivalence classes for the domain of each variable. I'm sorry, but here there are one line here, one line here, one here. So we have 1, 2, 3, 4, 5, and 6 areas. I know it doesn't show on the slide. When I will give you the PDF, you will see it. Stay with me, possibly. So we want to cover at least one of the classes for each of the direction. If we divided the interval AB in two classes, from this direction, for every time we test, we want to cover at least one of these classes. So we are covering the highest, the lowest, the highest with this tree. And from this direction, we want to cover at least one of the other 3 classes that we have here. So we cover 1 and we cover 2. How many test cases we need to do here? Well, the maximum between and n. So the minimum number of tokens, test values, in a grid, which is n times n, such that each row and each column contains at least 1 token. It's like covering with the chessboard with queens, something like that. It's also called the equivalence or category partition method. For our example, the values we can divide in these kind of sub-intervals. 1830, 3135, 3640, 4145, and so on. The salary, just take one value, it's okay. And the male is strange as a boundary value because we know that booleans just have 2 values, so we check both of them. And here we have the same thing as before. If we want a more strong coverage instead of a big one, we put a token not at least 1 for each class, but for every class. So instead of having that the number of tests that we have to do is the maximum between an n times n grid is n times n. Right? And as you can see in this case, we have more fails that arise. Then, an oxymoron, a weak, robust coverage. Weak because it adds out of range test cases. So for each of the possible intervals, we do not just take values that are inside our range, but also values that are outside our range to be more robust. So we have to add 2 times n values. Sorry for that. But these are the output, and this is if we, and these are all fade in this case. If we combine both the strong normal and the weak robust, we obtain the strong robust coverage, in which the number of test cases is the production of the sum, the number of intervals plus 2 for each variable. Okay? We can even combine all of these with the robust of the first one and the robust of the second one. So we obtain this kind of number of sample points. The number of test cases in this case is abnormous. Is the productory of 4 times the size of each interval plus 1. In the telescope for the Morse gauge, we have more than 100 test cases, but it catches all the 12 parts that were in the code. So it's good. But there are too many for every kind of real-life program. Why? Considering 5 variables, which have 5 possible partitions or subset each, then we have 8 million test cases. Obviously, we do not assume to use 1 second for each test case. We can have much less than this. But considering 1 second for each test case, we have spent 3 months of pure computer testing for just 1 function. Okay? So, for some kind of, let's say, very strict function that we need to check consistently because it's the base of the whole system that we are constructing, something like this can be used. Otherwise, we should use the previous one. Okay? We still have some kind of problems because we do not have constraints on equivalence classes. Who defines the equivalent classes? If they are not defined by requirements, we do not know. We also have to consider that we have dependencies among different variables that we didn't take into account in this case. And we are applying worst case testing on some boundary values that probably doesn't need to apply. We just have true and false. We do not have to have more than true or less than false value in our study. So, that's it for today.